So in this short movie, I'm going to give you an introduction to an important algorithm in molecular modeling, which is known as TLC, which stands for Tripeptide-loop-closure or Triaxial Loop Closure, as this algorithm is also used in robotics. So I'll be using the TLC solver from the Structural Bioinformatics Library, launched from VMD2, and therefore I'm going to plugins, SBL, TLC. I get the GUI, and I'll be using the variable domain of an antibody here, and so I'm loading one vfb.pdb, focusing on chain A, and for a minute we'll be considering 3 consecutive amino acids, which are 11, 12, 13. So I'm launching the calculation, and within seconds I'm getting a solution set in the graphics engine of VMD, and as you can see we have 6 solutions here. So let me re-explain the configuration. So we have 3 consecutive amino acids, so the purple one to the left, the middle one in green, and the pink one on the right hand side. The bullets correspond to the C-alpha carbons, and so the problem solved by TLC is precisely the following one. So we keep these 2 segments to the left and to the right, which I'm going to call the legs. We keep the legs fixed. We also keep fixed the bond length and the valence angles, namely the angles found at the vertices of any 2 consecutive bonds. And on the other hand, we are going to be able to change torsion angles, and precisely 6 of them. And so here, the 6 angles which can be changed are the phi and psi angles associated with the 3 C-alpha carbons. And so in fact, TLC is precisely enumerating all possible conformations by changing 6 torsion angles while keeping fixed the 2 legs on the one hand and the remaining internal coordinates, namely bond lengths and valence angles, on the other hand. And so what is remarkable here is that, as you can see, the conformations which are generated are massively different from one another, which is completely different from what we get when running molecular dynamics, where consecutive conformations are highly similar due to tiny time steps in the simulations. So, of course, from the VMD graphics engine, we can select or deselect the conformations, and interestingly, as you can see, the first solution corresponds to the structure which has been given as input, and the remaining ones correspond to, in fact, the solutions of the TLC problem, and it can be shown theoretically that there are at most 16 solutions. These solutions are actually given by the roots of a degree 16 polynomial. Okay, so let's replay this example now by focusing on non-consecutive amino acids, for example 11, 13, 15, and let me run the calculation again. And so now it turns out that we get 3 plus 2 plus 3, 8 solutions. The number of solutions is even in general because, as I told you, conformations correspond to roots of a degree 16 polynomial, and in fact, when this polynomial is crossing the axis y is equal to 0, it does so in a way such that solutions come into pairs. And so here we have these 8 solutions, and as you can see, they are massively different from one another. So this is a TLC algorithm which can be used to generate conformation highly different. And of course, there are a number of limitations. So the first one is that, as I told you, we are playing with 6 torsion angles only. And of course, there is one question, which is to generate or to use this algorithm for much longer backbone segments. And so we have generated one model for this. It is available also in the SBL, and it will be presented in another video. And the second caveat or limitation is that we generate backbone conformations, but we don't have side chains. And so it means that in order to control steric clashes, we have to find the rotamers or conformation of the side chains compatible with one another and also with the rest of the protein structure. And so this can be done in 2 ways, essentially. The first one is the usual way followed in inverse folding or protein design. It usually boils down to solving integer linear programs. And the second one consists of using transformers, as done in the structure module of AlphaFold. And to conclude, as you can see, there is an output directory there, and so if you go in this output directory, you will find the structures which have been generated, and here one structure for each solution.